based on students' questions last class, I thought it would be useful to put everything in context. Where are we right now after 3 classes following the introductory class? So only 3 class periods. In the next slide, we'll see where we are. We've had about 2.5 classes of introductory material. And why did we study this? Well, because it's waves, we wanted to study why what is a wave is important. Well, why it's important is because when we have the basic idea of translation and take it forward, then we can apply it to all the different wave objects that you see listed. In the next slide, I'm going to address the question that was also asked, why did we use transmission lines? Well, transmission lines are a great way to start, and the reason that is so is because transmission lines are essentially one-dimensional structures in space, and they are the first and simplest wave object because as you look at that list, the one at the bottom that's highlighted in big bold letters in white is application of reflection and power delivery. In other words, they're actually used to carry power and information. So that application of using transmission lines sets us up for other applications, notably reflection in optics and power delivery in power transmission lines. In the next slide, we address what have we learned. Well, the first thing that we've learned is we've learned that by the application of simple translation, we can write a wave traveling to the right as f of x minus vt, and a wave traveling to the left as g of x or z plus vt. Now, the uniform translation is really important because we build on that. Well, the first thing we do is we find out what kind of differential equation do those one-way functions have. And so we see that in item 2. Now, if we have waves traveling to the right, denoted by f of z minus vt, and waves traveling to the left, denoted by g of z plus vt, and they're added together to form what we called in class a function u, or the voltage as a forward wave and a backward wave. In terms of the voltage v, we get a second order equation. In other words, the function that goes to the right gets differentiated using one of those one-way wave equations, and the function traveling to the left, that would be g, uses the other one. So you actually have to do the operations cascaded twice, as we studied in class, and that gives us the two-way wave equation. Why do we want a two-way wave equation? Well, in order to answer that and justify it, we have to look at Maxwell's equations. That means 3 dimensions, vector calculus, and a whole bunch of vector identities that are not common knowledge to get the wave equation. So let's do it in a simpler way. Furthermore, we've learned wave properties and also how we deliver power along a transmission line. In the next slide, we see how we've done this. Well, if you look at the list, most of those items are all previously done. Complex numbers, complex exponentials, solution of that straightforward second order ordinary differential equation in terms of exponentials, e to the plus or minus gamma z. And we applied circuit knowledge, KCL and KVL, to get the waves arising out of an equivalent circuit to the Maxwell equations. That's really the way to describe what we've done. And of course, we've used calculus, and most importantly, the chain rule to get the one-way wave equation for functions traveling, for waves traveling to the right, f of z minus vt, waves traveling for the left, g of z plus vt, and then from there we built the second order wave equation, which has waves of both going to the right and to the left, and that's important because in real life you've always got waves going out and coming back, and they exist simultaneously to create interference and other patterns, and that's really important for actually manipulating waves in optics. So I hope that clarifies some of the issues raised, and I'm always open to having your feedback on how to improve the general context of where we're headed. Thank you very much.